evolution equations. And his work has been had a profound impact in modern theory of continuous semigroups and application to differential equations, mathematical physics, and dynamical systems. And today he's going to talk about positive semigroups, countable spectrum, and a cell growth model. Thank you very much, Professor.
Well, thank you very much for the very nice introduction, and thank you very much for inviting me to this talk. Well, I have best memories to the Universidad Federal Fluminense. Oh, it's difficult to to pronounce for me. Now, I have still to make the link. Oh,
Great. Yes.
I'm very sorry.
It's okay.
Okay, so I start right away with the talk, and I tell you my motivation a little bit later. So let T be a strongly continuous semigroup, and this is just a mapping. Each TT is an operator, and we have the semigroup property, and it's strongly continuous. Now we say that T has relatively compact orbits if each if each orbit is relatively compact. And this is somehow the theoretical framework I will talk about. One consequence is the semigroup is bounded. Now, if we have a bounded semigroup, we can distinguish two spaces. One is a space of all x such that ttx tends to 0 as t goes to infinity. This is a closed subspace invariant by the semigroup. And the second space, this is the closure of the span of all unimodular eigenvectors. So the span of all x, for which exists eta in R, such that ttx is equal to e to the I eta tx. Can you see the slides? Well,
yes, it's perfect.
Okay, good. Now, this space is interesting because we call it the reversible space, because on this space, the operators are invertible. In fact, there exists a strongly continuous group, I call it U, on this subspace XR, such that the restriction of TT to this subspace is U of T. Okay. But now, I mean, the question is do we cover the entire space plus X0 and XR? The intersection of these two spaces is 0, always. It's not obvious, but it's true. And then here's a theorem. I mean, this is a known theorem due to Glicksberg-Delisle. The following are equivalent. A semigroup has relatively compact orbits, and T is bounded, and X is the direct sum of X0 and XR. And this is an interesting situation. First of all, let's give one criterion. If the resolvent is compact and the semigroup is bounded, then we have relatively compact orbits. This is a quite frequent situation. Now I recall some notions. The generator of the semigroups, this is just the infinitesimal generator. It's an unbounded operator. It's defined as AX is the derivative of the semigroup at 0, and the domain of this operator consists of all x such that this limit exists, such that this derivative exists. And then given x, the orbit of TTX is the unique weak solution of the Cauchy problem. So U dot equal AU of T u of 0 equal to x. It's a weak solution. So it is interesting to find out when a given operator is a generator of a semigroup, then we have well-posedness of the Cauchy problem. Of course, parabolic equations with all sorts of boundary conditions are an example, but we will see others. Now, what I also should recall is if we have the generator of a semigroup, so this is this operator A, then the resolvent exists for real lambda larger than 0. So the resolvent is lambda identity minus A power minus 1, and we assume that T is bounded. The resolvent is given by the Laplace transform. And we also need the notion of the spectrum. So the spectrum is those lambda such that lambda identity minus A is not invertible. Invertible means to have an inverse which is a bounded operator. Lambda minus A is an unbounded operator. It's only defined on the domain of the operator. We ask that the mapping lambda minus I is surjective and the inverse is a bounded operator. So this is a resolvent set, and the complementary set is a spectrum. Okay, the point spectrum, these are just the eigenvalues. So the lambda such that there exists x in the domain different from 0 such that ax is lambda x. And this is the same as saying ttx is equal to e to the lambda tx. We should remember this for the following. Now, let's now a much more subtle result on this relatively compact orbits is having countable spectrum. So if X is a reflexive space and T is bounded, and if the spectrum on the imaginary axis is countable, then T has relatively compact orbits. Well, this is a theorem from some time ago jointly with Charles Beatty, and independently proved by Lubitsch and Wu by very different methods. Anyway, so I want to take this theorem as a basis because, well, it marries well. There's a beautiful marriage with positive semigroups. So now I come to positive semigroups. So E, now I call it E, no longer X, is a Banach lattice, but we may imagine throughout that E is LP. This is for all applications I have in mind, this suffices. So we call T eventually positive if there exists T0 such that Tt is a positive operator for T larger or equal than T0. And a positive operator is in the sense of, well, the order structure of LP. So this means if V is larger or equal than 0, then also TV should be larger or equal than 0. And V being larger or equal to 0 means to be larger or equal than 0 almost everywhere. Now, what is new today and for some years now is this notion of eventually positive. Because a long time ago, we wrote a book on positive semigroups, and recently we did a second edition, so this will appear very soon. So this is one reason why I was thinking again about these positive semigroups. But then some time ago, this eventually positive occurred. So this means the semigroup is only positive starting with some T0. And it came out by considering the Dirichlet-Neumann operator. And we noticed this generates a positive semigroup in some cases. And I had a conjecture, and Daniel Danners disproved this conjecture. And he discovered at the same time that in some cases, the semigroup is eventually positive. And then a theory started, and the leading figure is Jochen Glück in Wuppertal, and well, he and many others derived a theory of eventually positive semigroups, and turned out that there are many examples. And so there are many reasons to look at this more general notion of eventually positivity than to positivity. Now, what I want to explain you in this talk is, I think, some beautiful results on spectral theory and asymptotic behavior of positive semigroups. And then I will give applications to this. So the following theorem is due to Greiner in the case of positive semigroups, and to Aurora for eventually positive semigroups. It says that positivity, or even only eventual positivity, implies some regularity of the boundary spectrum, of the spectrum on the imaginary axis. It is cyclic. So if I eta is an element of the spectrum, then also I n eta is in the spectrum for all n in Z. So this is a very a certain regularity or geometric property of the spectrum of a positive bounded semigroup, or eventuality positive semigroup. I should say, I mean, this is a quite deep result, and Aurora proved last year that it remains true for eventually positive semigroups, and there additional ideas were needed to prove this. A quite clever idea. Now, I talk about another hypothesis. We call the semigroup eventually norm-continuous. Well, if it is norm-continuous starting with some T0. There are many examples. I mean, all parabolic equations lead to such semigroups. Holomorphic semigroups have this property. A consequence of this is the spectrum on the imaginary axis is bounded. This is for eventually norm-continuous semigroups. And now here comes the first theorem. I call it the stability theorem. So there will be two theorems on asymptotic behavior for positive semigroups, or eventually positive semigroups. So the first is this stability theorem. And then I talk about another one. So the stability theorem says the following. We assume that T is bounded and eventually norm-continuous and eventually positive. So if the spectrum on the imaginary axis is countable, then the limit TTF as T goes to infinity exists for all F in E, for all F in LP. So remember, the orbits are the solutions of the Cauchy problem. So this means, I mean, this Cauchy problem is stable in this sense. The solutions converge strongly. Okay, so this is true if the spectrum is countable. And it would also be true if I merely assume, if I assume more generally that, that the orbits are relatively compact. But I emphasize a little bit this countability condition, because in the second theorem you will see it is it's even a little bit nicer. Okay, so this is the stability theorem. Later I will apply it to cells, to cell growth. You see, okay, oh, maybe I give the proof, because now after what I have said, the proof is I can give it directly. So the spectrum on the imaginary axis is bounded and cyclic. So bounded and cyclic implies it is reduced to zero, because it cannot, otherwise there would be infinitely, I mean, many points going to infinity. Now, if TTF is equal to e to the eta f, this is the same as saying AF is I eta f. So if eta is if eta is different from 0, then also n eta would be an eigenvalue. E to the I n eta t, there would be an f. So we would have I eta n t. So this cannot be. So eta is the only eigenvalue. So this means TTF is equal to f for all f. I mean, no, I say it again. We consider this space. Here I have a nice tool. Oh, shit. I say it again. We have this space here, ER. Now, this space ER, in our case, is just the F such that TTF is equal to F. Because TTF e to the eta TF, the only eta possible eta is eta equal to 0. And so we have TTF for all F in RE. Now we know E is the direct sum of E0 and ER. On ER, the semigroup converges to 0. So TTF converges to PF, and P is the projection onto ER along this decomposition. Okay, so this is a proof. I mean, we put together two results. One is the boundedness of the imaginary spectrum, because the semigroup is supposed to be eventually norm continuous, and the cyclicity of the spectrum. We put together these two results. Now, there are many examples for this. Well, the most simple is probably the Neumann Laplacian, the Laplacian with Neumann boundary conditions on L2 or even on L1, which is more natural. We need Lipschitz continuity for the boundary. But now, if we considering eventually, or since eventual positivity is allowed, we can also take minus the Laplacian n square. And this is remarkable because for the Laplacian square, we don't have a maximum principle anymore. So things change quite a lot. Just to give you a name, I mean, this spectral theory of positive semigroup together with asymptotic behavior, we call this Perron-Frobenius theorem. Because Perron and Frobenius in around 1910, they developed such a theory for positive matrices. And this is an extension of this series to unbounded operators instead of matrices, which is much more complex and more difficult, of course. Now, I come to another notion which is important in this context. This is a notion of irreducibility. We need the notion of a closed ideal in the lattice sense. For LP, it's easy to define. It's given by a measurable subset of omega, and J consists of all F in LP such that F restricted to the complement of B is equal to 0. So such an object is called, or is a closed ideal in LP, and all closed ideals are of this form. We call the semigroup irreducible if whenever T0 is larger or equal to 0 and TTJ and J is invariant for T larger than T0, then J is trivial. So J is the entire space or J is 0. This is the notion of irreducibility. You see, just to mention it, in the stability theorem, if the semigroup is in addition irreducible, then we have a rank 1 projection here. So this is very interesting. So it converges really to an equilibrium. So irreducibility is nice. For our example, the Laplacian, the semigroup generated by the Laplacian is irreducible. So it's an example. Okay, so we have this notion of irreducibility. And here's a next result next spectral result, I mean, on geometric properties of the spectrum of a positive semigroup. So if T is a bounded, irreducible semigroup, which is eventually positive, then the point spectrum of A on the imaginary axis is a subgroup. Not only irreducible, not only cyclic, it's even a subgroup. This was proved by Greiner, but it extends to eventually positive semigroups by some arguments. Okay, so let's exploit this property, the subgroup property. Okay, and here's already a theorem, or the basic theorem. I call it the periodicity theorem in this talk. So T is a bounded, irreducible, eventually positive semigroup. But now it's no longer eventually norm continuous. I mean, not at all. This is somehow what we will see now. This is somehow complementary to what is happening for eventually norm continuous semigroups. So we assume two things. The spectrum is again countable. The imaginary spectrum is countable. And we imagine that we suppose that there's some alpha different from zero, such that I alpha is in the point spectrum, is an eigenvalue. Okay, and then we have again the same result. E is the direct sum of E0 and ER. On E0, the semigroup goes to zero. But on ER, the semigroup is periodic. This is the special thing. The semigroup is periodic. So it's the restriction of a periodic group on ER. And now we want to prove this. I give you a proof of this result. This is a consequence of what we said before. So here's the proof. So the point spectrum of A intersection IR is a subgroup of IR. Of IR with I mean, a group for the sum, for the additive group. So the closure is also a subgroup. Now, the closure is contained in the spectrum intersection IR because the spectrum is closed. The point spectrum is not, or not, in general not, but the spectrum is closed. Now we have a subgroup of IR, which is different from IR, but which is also different from zero, because we have this I alpha, which is an element. So it must be of the form a multiple of Z, I times a multiple I times a multiple of the integers. And I write the constant we obtain as 2 pi divided by tau. This is just, instead of writing some number, I write 2 pi divided by tau. So since the closure has this form, so the closure is discrete, the group itself must be the same. It must be discrete itself. So sigma p of A, the point spectrum on the imaginary axis, is just the set I 2 pi divided by tau Z. Now, ER is the span, the closure of the span of eigenvectors belonging to this set, this point spectrum on ER. So for such a vector, TTX is e to the I 2 pi divided by tau mtx. Because you see, an element of the spectrum is, this is a typical element of the spectrum. I have to multiply with m with an element m in z. But now you see, this is equal to x, because m. So this means tt plus tau x is equal to ttx, because if we have t equal tau, then we have 1 here. So for t equal tau, this number is 1. So tt plus tau x is equal to ttx for all x in ER. In other words, the semigroup is periodic, and then also this group which extends the semigroup. So we have a periodic semigroup. And I think this is quite beautiful, a quite beautiful application. So it means, morally, I mean, the semigroup converges to a periodic group. I mean, or I could say it differently, for large time, the semigroup is periodic. Okay, so this is the periodicity theorem. Now, such periodicity phenomena can be observed in models. One model I know is a network, and this would have fit with the previous talk, but I don't want to talk about this network. Another example is given by cell division. And maybe now, after this more theoretical part of the talk, I want to present a model and show how these things can be applied to a model. So I will talk about evolution of a cell population. So cells, they reproduce just by division. So this is a very special way of evolution. So how is this modeled in mathematics? So we consider a population of cells that are distinguished by their individual size. So the size may be the diameter, or it might be the volume, or it may also be the content of proteins or something like this. But it's a number. So we imagine the size as a number. Maybe we imagine the diameter of the cell. And then what we observe, UTX, this is a number of cells of size X. Now the size is always as a minimum size. All cells, I mean, you don't observe arbitrarily small cells, and you don't observe arbitrarily large cells. So we assume that our cells are in between 1/4 and 1. This is just to have a concrete number. So the size is a number between 1/4 and 1, X. Now, to say that UTX is the number of cells is not exactly what I want to say. It's a density. So the integral of x1 to x2 of UTX dx is a number of cells of size in the interval x1, x2 at time t larger than 0. This number we want to study. So we want to see how this develops in time, the evolution of this number. We want to understand the evolution of this number. Okay. Now, first of all, cells grow. And they will grow maybe following a certain law. So we assume that x dot is equal to g x of t. And g is a C1 function, which is positive, so they really grow. So x dot is, x is increasing. X of t is increasing in time. So a good model is already G equal to 1. G equal to 1, then we have linear growth. Linear growth is quite reasonable, I think. Now, we consider for given an interval, in our interval a quarter and 1, we consider a subinterval. And we will consider arbitrary subintervals. And on such subinterval, we count how many cells are there which have size in between A and B. So this is n of t. N of t is the integral a to b, a u of tx dx. This is the number of cells of size in AB. Now, an important thing is cells do just grow, but they don't produce new cells. They grow, and for the moment, we don't talk about division. We just talk what the cells do. So they just grow, and there are no new cells created somehow, or cells do not disappear. So this means the changement of n dot of t of n of t comes only from cells leaving the interval AB. So n of t, now you see we fixed an interval a of b. Now if n of t, so the number of cells in A and B in this interval, this just changes because some of the cells grow and go out of B, become larger than B, and others are smaller than A and come into A. So n dot of G is minus G of B UTB. So G of B is the rate of increase. When a cell has size B, then it increases by G of B. So we have UTB cells, and then, GB U of TB cells will go out of the interval. On the other hand, G of A UTA will come into the interval. So n dot of t, I interchange integral and derivative. Here is the definition of n. So I interchange here derivative and the integral. So n dot of t is the derivative in time of u of t. And now you see, this is the same as this. This I can write also as the integral of d to the dx of g of x utx dx. So we derived the following equation. Since this is true for any subinterval, we have a partial differential equation, du dx dt is equal to minus d to the x g of x utx. And this is called the continuity equation. It's just a conservation law. No new cells are produced and no cells disappear. This is a conservation. That's all. Now, okay, so we accept this conservation law. Now we add other assumptions from our model. So the next assumption is some of the cells die. And we call the rate of the death rate mu of x. And then we obtain the differential equation du of t is equal to minus this term as before, but minus mu of x utx. This is the death rate. Now comes the most interesting thing, the division of cells. So each cell divides into two cells of equal size. This is what we assume. And not all of them do it at once. They do it at a rate b of x. So it's a density, b of x is a function, and the rate, the proportion of cells which divide, this is b of x. This gives the following the following equation. So again, we have the derivative with respect to time is this term. This is just conservation minus the death rate. Now, a cell, if a cell divides at the rate b of x, we lose cells in our interval. And we add cells which had before the size 2 of x. Now they come, we win these cells of size x by division of cells of size 2x. And this is this term here. If x is larger than a half, nothing happens. There are no cells of size 2x. If x is smaller than a half, then a cell of 2x gives us this new term. And actually, you see, the form may surprise you in the moment, but we get 2b of 2x ut of x new cells because division in two parts. But they also are in a smaller, we also have to take care of the interval. So before we had an interval of the double size, and now if you do substitution, you will have another 4, another 2 here. So this gives 4. Notice UTX is a density. So this is the equation which governs cell division with also some death rate. Okay. Now, we apply semigroups to this situation. We define E to L1 a quarter 1. The domain of the operator is all functions in W11 a quarter 1, f of a quarter is equal to 0. W11, this is the first Sobolev space. So we have L1. L1 is not reflexive. I'm aware of that, but this is the right space because the norm of L1 for positive functions is exactly what we want to know. This is how many cells are there. This is given by the integral. The operator is AF is equal to minus GF prime. You see, this was, here we have minus d to dx, g of x, u dx, minus mu plus bf. This is this term. And finally, we write this as a new operator. It's a bounded operator defined in this way, where b is this given function which which tells us the rate of those cells which divide. Now, assume that G has these properties, and then we have a theorem. Then A generates a positive irreducible semigroup, and if the spectral bound is 0, so this means the largest eigenvalue, this semigroup, well, no, it's not the largest eigenvalue, but it's the largest spectral value. S of A is 0. This is somehow a normalization. Then TT converges to a rank 1 projection. Okay, and in this case, the semigroup is eventually compact, so it's eventually norm continuous, and we can apply our stability theorem, and this gives this result. So interpretation is the following. If we fix an interval AB, and if we have an initial number of cells in the interval given by F, so this is the initial number of cells at time F, then at the end, after a large time, after some time, the new distribution will be this. So it gives, so the evolution is to a fixed distribution. So for how many cells you have of size, I don't know, of size x1 and of size x2. This is fixed after some time. Or otherwise stated, if this is a rank 1 operator, so if you introduce this as an initial value, then it becomes constant. Then the size distribution is constant. Okay, now I just tell you there's also a situation where we have convergence to a periodic group. But it is a little bit more complicated to interpret. But well, maybe. So in here, I mean, in this theorem, it's a little bit the g of x. The g is 1. The g is 1, but this operator has been transformed. There's a transformation from the original equation. And then one obtains this situation. One obtains this operator A0, which is, well, the semigroup is easy to write down. And then we have this kind of perturbation. And here I call it K, what was B before, but the K is special. And also the L1 space is special. There's a special weight. And then the assertion is the following. There exists a continuous weight such that this operator, A0 plus B, as before, generates a reducible positive semigroup. This semigroup preserves the norm for positive elements. It should preserve the norm because we want that the distribution remains stable. The spectrum is countable, and there exists an alpha such that I alpha is in the spectrum of A. So in this case, the semigroup becomes eventually periodic. So we can apply this theorem. Well, I'm at the end of my talk. There's another. I had another remark on these eventually positive semigroups concerning elliptic operators to convince you that there are other very surprising examples. But I hope I could tell you that this Perron-Frobenius theorem has some beautiful theorems which also lead to results for models. Thank you very much for the attention.
Thank you very much, Professor Wolfgang. Thank you very much. I'd like to ask you if there's any biological corresponding to this convergence to the periodic semigroup or something like that.
The periodic semigroup, yeah. You see, I must admit, I understand this. Biologically, I don't understand really. I mean, or I was not able to find an answer to this question, which I was accepting when I was preparing this talk. There are many papers on such things, but this periodic phenomenon is a little bit hidden. So I can't explain a biological. Sorry.
It's always complicated for us to fully understand the real world thing, I believe, for us mathematicians, and that's what we struggle with. And yeah, me too. Another of my doubts, I would like to know if you have thought of quasi-periodicity or anti-periodicity or something like that, if you think it's possible to adapt your results to that setting.
now I'm
like if you have in the like t for t plus tau equals t, big T of t, plus a constant plus something like that, just to perturb periodicity a little bit, and yet you get similar results.
this I don't know. Quasi-periodicity, I don't know. Almost periodicity is this fits into there's a theory of almost periodicity, and this countable spectrum things, they are part of the theory of almost periodicity. But quasi-periodicity, I must say, I'm not so acquainted with.
Yeah, because I think there are some, I like some definitions of, some more general definitions of periodicity, and sometimes they just fit what we did just like nicely without too much change. So that was why I was asking for you that.
Yeah. This is a good suggestion. I will look it up. I will look up.
Yeah, I saw this theta periodicity, and this theta function would be something like, if it's the identity, it would be periodicity in the original sense that we know. If it's minus the identity, it would be anti-periodicity or something like that. I think sometimes this kind of stuff can fit just like perfectly.
Okay. Yeah. Well, thank you for the suggestion.
Would you like people to make any observations or questions? And Professor, what if we look only at this eventual positivity? Do you have similar results if we suppress some of the conditions, or I don't know, anything like that?
Well, you see, the thing is, this is already quite surprising that for me, it is surprising that these things work for almost for eventually positivity, because we leave usually these elliptic operators of second order. If you have an operator of fourth order, it is never generates a positive semigroup. This one can prove.
That's great.
But also, what we discovered, if you have elliptic systems, I mean, this is a classical theory, classical subject in PDE. I mean, elliptic equations, they have very nice regularity properties like the Georgi-Nash or so. But for systems, it's false. This is known. So it's known that systems have very, I mean, not so good properties. And we know it also for positivity. We know a system generates a positive semigroup only if it decouples. So it's just independent equations. You have n independent equations which each have positivity property. This is the only way it can be a system can be positive, but it can be eventually positive. And so we have the spectral properties. The spectral properties are quite are interesting because they lead to some asymptotic behavior. Otherwise, I mean, you are, of course, I mean, there's no entire theory. I mean, these notions are completely analyzed and maybe also generalized. This is to this. Jochen Glück, who even is writing a book on this. So there's a lot going on. But more interesting is the examples. I mean, which examples are there? But there are interesting examples.
That's great. I loved your talk. And I love also the fact that the back of your slides are black, and written in white because all my windows here are like that. So
Yeah.
I like it very much. Thank you,
Yeah, but
Professor.
you see, it's meant to be a blackboard talk.
Okay.
Marcia,
But
in the chat
what I did do,
question.
okay.
Well, thank you to all of you. We will pass to our next speaker today, Manuel. Please, you can start sharing your slides to